Okay, this is topic 5.2 from the A2 CCEA Chemistry, and it's the answers to the fact file for nuclear magnetic resonance. So it's NMR. Question 1. Nuclear magnetic resonance spectroscopy, or NMR, is used to help understand the structure of molecules. TMS is the standard used in NMR. What is the chemical name for TMS? Well, it says name, so you have to give name, so it's tetramethylsilane. Remember, if it says name, give name. If it says formula, give the formula. Give 2 reasons why TMS is suitable for use as a standard in NMR. Well, the first one is all of the hydrogens are equivalent. So they're all in the same environment, which means they only give one peak. And the second reason is that TMS is inert. Or you could say that its signal is outside the usual range. Okay, or you could say all of those things. It doesn't say on that, but the marking, there's 1 mark for the name tetramethylsilane, and then 2 marks, 1 for each reason in the second part. Now, this is a nasty question, I think, 5 marks, and it's quite tricky, so let's just go through it quite slowly. So sketch the NMR spectrum for methyl propanoate, showing the integration curve together with splitting patterns, and indicate which hydrogen atoms are responsible for each peak. So I've written out the formula here for the methyl propanoate, so we can see it a bit clearer instead of up there in the tiny writing. And then I've just identified the 3 separate environments for the hydrogens. So there's one here in this methyl group, an ethyl group, and then we have the methyl group at the other end. Okay. So in terms of the integration curve, it's going to be 3, 2, and 3 for those, because we have those are just the numbers of hydrogens in each environment. Then when we look at the splitting patterns, this methyl group here, that's going to be a triplet because the adjacent carbon has 2 hydrogens on it. And remember your n+1 rule. Then the CH2 group here is adjacent to a carbon with 3 hydrogens on it, so that's going to be a quartet again. Remember your n+1 rule. And at the end here, the methyl group right at the end has no hydrogens on any adjacent carbons, so there will be no splitting for that one. So we have a quartet, a triplet, and one with no splitting. So the way this is marked, you're going to get 1 mark for the correct splitting, 1 mark for the integration curve being correct, and then the other marks are for each set of peaks having the correct height, the correct shift, and being labelled. So I think the easiest bit is the splitting, and then the size of the integration curve. So I've drawn it here, I've got 3, 2, 3 on there. But the hardest bit is getting the peaks in the right order. So when we look at this, we have then the CH3O peak is going to be at the highest value, so the furthest to the left because it's de-shielded. Then we have the CH2 one, which is beside a carbon which has an oxygen on it, so it's going to be de-shielded a little bit. And then the lowest value is going to be from the methyl group in the ethyl chain. Okay, I hope that makes sense. So, next question. The first person to extract ethanoic acid from vinegar was the alchemist Jabir ibn Hayyan Geber. Apologies if I got that wrong. 721 to 815 AD. However, the pure compound was not produced for another 10 centuries. So the mass spectrum of ethanoic acid shows a distinct peak at 59. State the formula of the species giving rise to this peak. Well, the formula mass of ethanoic acid is 60, so the species is just taken away 1 hydrogen, which is CH3COO+. Then it says it reacts with ethanol to form the ester ethyl ethanoate. The NMR spectrum consists of 3 peaks as shown. So what I've done is I have drawn out, or I've written out the structure. So instead of just CH3CO C2H5, I've got CH3 COO, CH2, CH3, and that makes it easier to see where those peaks are coming from. So explain the peak integrations. So we've got 3 hydrogens in this environment. We have 2 here and 3 here, so it's going to be 3 to 2 to 3 for the ratio because of 3 different environments, and it's just as simple as saying that. Okay, so 3 to 2 to 3 because of 3 different environments. Then explain the chemical shifts, and this is why I've colour-coded it up here. So the first one, the quartet, which is here, is high value because it's near the electronegative oxygen. So you see that the oxygen in the molecules right beside it. The intermediate value singlet is close to this, so it's this one, and it's here, and it's close to the carbon bonded to two oxygens, but it's not directly bonded to an oxygen, so it's not as de-shielded as A. And then the lowest value, as the green one here, is just the methyl group in the ethyl chain. Okay. So then explain the splitting pattern in A. Well, it's split by 3 chemically equivalent hydrogens on the adjacent carbon, so it's a quartet. And then explain why B is a singlet. So let's just go back and look at that. So here is, let's see, get a different colour. Here is B. Okay, so why is B a singlet? Okay, it's because there are no hydrogen atoms on the adjacent atoms. I'm just going to go back to that again. So you see here, it's this one, this. So the carbon next to it just has 2 oxygens on it, so it has to be a singlet. Okay, back to this page. The NMR spectrum of compound, that should say compound, it says compound, but we'll ignore that, is shown below. Which one of the following is X? So looking at the NMR first, we have 3 different environments here, so 3 peaks. And this one here is a triplet, so that must mean it's beside a CH2. This one is a singlet, so no adjacent hydrogens. And this one then is a quartet, so it must be beside a CH3. So we're looking for something which has those things in it. So the first one has 1, 2, 3, 4 different environments, can't be it. And then in B we've got 1, 2, 3, 4 environments again, and so no. So that leaves us with C and D, which both have 3 environments. Now if we look at C, there is 1 with no adjacent hydrogens, and then 1 which is adjacent to 3 and 1 which is adjacent to 2. So the answer is actually C. The reason it can't be D, actually, so there are 3 different hydrogen environments in D, but the singlet there would be from the COOH, and it would be de-shielded, so it would be higher value, so it would be coming in sort of above 4. Right, final question. The NMR spectrum of propanamide is shown below. So the signal at 0 is due to TMS. Explain why TMS is used as standard. So it's this question again. And it's all the hydrogens are equivalent, so you only get 1 signal, and it's outside the usual range. And explain why the signal at 1.15 is a triplet. That's this one. And the reason has to be the n+1 rule, so it's next to a CH2 group. Then explain why the signal at 2.25 is a quartet, and again the n+1 rule, so it's next to a methyl group. And explain why the signal at 5.5 is the highest chemical shift in the spectrum. Well, the highest chemical shift is generally, if it's up in this area, is due to de-shielding. So what do we have here that could be causing de-shielding? Well, it's the nitrogen. So the protons are next to the nitrogen, which is de-shielding, and that will get you your mark. Then explain 3 ways which this spectrum would differ from the spectrum of the N-methylated compound, which is CH3CH2, CONH, CH3. So if you look carefully here, there's 4 different environments, 1, 2, 3, 4. So there would be 4 peaks and not 3, in other words, an extra peak. The extra peak would be below the quartet. The integration ratio, if you look at the numbers, 3, 2, 1, 3. So that's what the integration ratio would be. And the chemical shifts of all the peaks would be different because they're in slightly different environments. So any 3 of those would give you your 3 marks. Thanks for watching.